So this is engineering statistics and linear algebra, and we were talking about the module 1, single random variables. Under this, we are taking the last topic, that is lecture 7, which corresponds to the condition RV. So condition just means that, you know, we have taken probability, conditional probability. Similar to the conditional probability, we have the conditioned, random variables, or we can say conditional random variables, whatever you call it, right? So similar to the probability of events, where we considered the conditional probability, we also have the conditioning of the random variables. Now we can consider the situation something like this: a random variable x is, defined first. We define the random variable, which refers to the, probability density function fxx. Okay, we know this. We have determined this, or we know this from the random variable x. Define this, and we know this. Then some event b conditions the observation of x. So there is some dependency of this with respect to the what you call some other situation. So that is, some observations of x are favored or suppressed with respect to the others because of the event b. So because of a particular event b, some of the observations of x are either favored or suppressed there. That means x is dependent upon b. So finally, a new PDF where we say f of x condition b of x reflecting the conditioned effect of b is found. This new conditioned PDF has all the general features of any PDF. That is, it has an area of 1 as required by 2.12, and it has an associated, the CDF. Okay, the CDF. Fx bx. This is the conditioned. This is the what you call cumulative distributive function. This is CDF that is there, and it can be used to find conditioned expectations like the mean, which is mu x given b. Sometimes we call it as condition b or given b, and a variance of sigma squared of x given b. Okay, so x is dependent upon b. X is dependent upon b, or what is the value of x given b because of its dependence is what we might be considering. So for some of the examples here are, you can have a what you call situation where we are considering a communication system with noise. Okay, so a PDF of the noise in the communication system might be different if thunderstorms are present rather than when the weather is clear. So when the weather is clear, the PDF of the noise in the communication system will be different. And the what you call when the thunderstorms are there, then the noise in the communication system will be different. Okay, so that is the dependency of the noise in the communication system because of the situation, condition of the weather, whether is clear or whether is having thunderstorms. Okay, so or you can consider the some critical application electronics, that is two resistors may be needed to be matched. We might need that two resistors are matched. So the event that the resistors are matched would then make the gain of the amplifier have a smaller variance than without matching. So with matching, the variance might be different. Without matching of the resistors, the variance might be different. Or you can consider manufacturing where we are putting guard bands to are used in the test measurements in order to reduce some variability that a customer might experience. So all this, this will be just you put guard bands for in the test measurements in order to reduce the variability that a customer might experience. So if you put more guard band, how much will be the variability? If you put less guard bands, how much will be the variability? Okay, can be checked. So the what you call variability of the measurement will depend upon the guard band. So guard band is like B, and the what you call measurement of whatever test which we are doing is the event which is X. Okay. So like that, you can have many different examples. You can think of your own examples also, right? So let us go forward, assuming that we are given a random variable X with its PDF and CDF. Further, assuming that some condition event B is also given to us, then B might be, for example, all observations in the range x1 to x2. So we will consider here B as in the range of x1 and x2. B is what you call within the range x1 and x2 of the X there, right? Then we define a condition CDF based on our previous definitions of condition events as fx b of x. So this is CDF, right? CDF is equal to P of x less than or equal to x intersection B by PP. So this is standard, Bayesian formula, right? This is the standard Bayesian formula. And whenever we consider the conditional, probability or conditional distribution, okay, probability or distribution both are same. So where PB is greater than 0. So using 2.113, we focus our attention on the events in the probability, joint probability, which is given over here. So this value, which is there over here, can be written as B. I can replace by this, and then it becomes this. Now, what are the values of X which we should take? So we'll have three different situations here. The first situation is if this, X is lesser than x1 itself. If X is lesser than x1, that is minus infinity, less than infinity, less than X, less than x1, minus infinity, less than X, less than x1. That is X is less than x1. If X is less than x1, there's no intersection between these two. So if there's no intersection between these two, effectively, then that will become phi. That will become phi. Now, if say X is within the same range as x1, x2, then naturally the what we call this value itself will be within the range x1 and x1 and x. Okay, then X less than X intersection B will be between x1 less than X less than or equal to small x. This is not be x2. Okay, because that will be within that range. Now, if X is greater than x2, if X value is greater than x2, then we are considering that, X greater than x2 means it covers all the ranges from what you call whatever is possible there here is also there in this if X is greater than x2. So therefore, we will get directly the value this itself, right? And that is B itself. X less than or equal to X intersection B, because it covers all of B, we'll get B itself. Okay, we'll get B itself. That means B itself means, B itself just means that, we are within this range x1 less than X less than x2. Okay, so here it is phi, here it is between x1 and X, here it is between x1 and x2, which is same as the B. Okay. Now we are considering here, we have written here the figure 2.15b, we have not shown that, and that just corresponds to the figure which is there over here. So this is our, random variable X, and B is say within this range, then we are talking about only this probability. Okay, we are talking about the, so more you extend it on this side and more you extend it on this side, then naturally it will be corresponding. So that means if the region x1 to x2, that is B, is somewhere on this side or it is somewhere on this side, there won't be any intersection. No intersection just means that no area at all, that is phi. If the range of values of this is, within this, then it will be corresponding to x1 to x, x1 to x. If the x1, x2 is totally encompassing the B, then B itself will be the range which corresponds to that. And that is what we have written over here. So applying these three cases to 1, 1, 4. The three cases which we are talking about is the three cases which we have written here, right? So these three cases, if we try to apply, then what will be the PDF is what is mentioned here. In the first case, it will be 0 for 5 between minus infinity less than x1. Then in the second case, between x1 and x2, then it will be this much, that is f of x minus f of x1. This will be a constant value, this will be a variable value, and divided by the probability of the conditional event, and 1 if it is larger than x2. So that's the standard format. And once this is the CDF, then the PDF will be just the differentiation of this function, that is d by dx of whatever we have written there. So if you differentiate 0, you'll get 0. If you differentiate 1 also, you'll get 1. If you differentiate this, then because this is a constant, you'll get 0 for this, and the differentiation of this will be small fx x, and hence we'll get fxx by pb within the range x1 and x2. So we will have, the equation 2.117 is typical of the PDF using choices for B other than the one given in 2.113. Similarly, the inverse of 2.117 will be fx bx is equal to, there we considered the differentiation. This is the differentiation of this. Rather, this is the integration of this. That is what is mentioned over here. Okay, if x of b, x is minus infinity to x, fx b u du. So that is CDF is the integration of the, what you call, PDF between the limits minus infinity and x. Similarly, you can have expectations conditioned by b. Okay, given b, what will be the expectation? Can be described as e of gx of b equal to integral minus infinity to infinity gx f of x of bx dx. This will be the case, general case. Now this general case will become particular when we write, the mean. The mean will be just the, what you call, g of x will be equal to x itself. If g of x is x, then this g of x should be replaced by small x. If g of x is x square, then we'll have f of x square fxb dx. Similarly, you can have the variance. Okay, this is mean. This is mean of the square, and this is, so to say, the mean, which is what you call, this is the mean between the with the, what you call, value considered over here. Okay, and that is why variance is generally considered as mean with respect to the what you call, already the mean squared with respect to this. Okay, so therefore we'll get the corresponding variance value also over here like this. Let us take an example here. A production line is designed to manufacture the resistors with the value 8,200 ohms. Assume that the production line is adjusted so that the resistors can be modeled as a Gaussian random variable with mean equal to this value itself and standard deviation equal to 650. Following the manufacturing, all resistors are measured and resistance have values within 5% of this 8,200, that is 8,200 plus or minus 410, are separated from the others to be marked and so on. So the condition event B is therefore this 8,200 ohms minus 410, that is this, and 8,500 200 plus 410, that is 8,610. So between these two values, that is the conditioning event we have. So PB will be naturally fx of 8610 minus fx of 7790. And if you want to calculate with respect to the mean and the variance given there, mean and the variance is, what you call, standard deviation given here, and the mean is given here corresponding to the standard deviation and the mean. We can try to find out 8,610 minus 8,200 divided by 615, and this is 7,790 minus 8,200 by 615. This is the standard way. So we can try to find out this from the tables which we have already considered in the what we call earlier case. That is the tables which are over here. You can try to find out those values, and the resultant will just be the one which corresponds to whatever we have here, 0.4950. So approximately half of the resistors produced by this just gives us that it is approximately equal to 0.5, that is 50%, and hence this is mentioned over here that approximately half of the resistors produced by the production line fall within the 5% of the desired value of 8,200. So the dependent probability density function, conditioned probability density function, will be fxx divided by 0.4950, that is the PB, between the range 7790 less than x less than 8610 and 0 otherwise. So the conditioned mean will be mu x of b is equal to 77908610x f of x b x dx. So we can just try to write that, and we see that again the mean will be same. Even for the conditioned case it will be same. Okay, so that is the conditioned mean is same as the original mean, because before any conditioning because the conditional PDF is symmetric about the 8,200. So it is symmetrical about the 8,200. We are taking plus or minus 8,100. If it was not there, then the mean would have differed also. But now because we have taken, around the exactly plus or minus 5%. On one side you have taken 4%, another side you have taken 5%. The mean is going to change, but because we have taken the what you call both sides, symmetricity. That's why the mean will remain same. But however, standard deviation is going to differ because we are going to stop it from appearing. That just means that if you go back to the figure which we have considered over here, if you see over here, right? So from the mean on this side and this side, if you take, the area will be, having the mean same thing. Whereas variance will be, we are just stopping at this point. We are not going out of that range. So definitely variance and standard deviation is going to change. So the standard deviation is, for the conditional variance will be sigma x of sigma square of x given b will be equal to 1 by 0.4950 root of 2 pi x, x minus mu x square. So this is mean there, x minus mu x square, and then the value of fxx. Okay, this should have been, the fxx divided by 0.4950 is f squared f x given b, fx given b of x, right? This divided by this quantity will be the what you call this value which we have written over here, and the rest is x squared. This divided by this value will be f of x given b. Otherwise, only this is the value which is f of xx, right? This divided by the 4.90 will be this value, and this is because of the mean which is centered at px. Okay, so if you substitute all these things over here in this and try to integrate this over there, right? Again, then we will get the what you call value as 52.775 of x. Okay, 52.775 of x. That means you can try to find out this value minus 2 by 3 and 2 by 3. This range you can try to find out by seeing the what you call table. So one side you have 0.66666, another side you have minus 0.666 and plus 0.666. So that will be the probability, density value over there, and hence we will get, we will get the corresponding value whatever we have, and we'll get the value which is 52775. 52775. If you take the root of this, then you'll get 229.7. 229.7. So effectively, it just means that, if you take this value, we might get the, earlier it was 615, now it is 229.7 only. So earlier it was quite large, now it has reduced quite a lot because of the restriction of the range of values between plus or minus 5%. Okay, so that can be easily computed for the values which is minus 2/3 to 2/3. Okay, so 0.666 is what we do. That means we can go back to the table there. So where is 0.666? So that might be somewhere. This is 66. Is it 66? Okay, 0.66. This one, somewhere between these two. Okay, somewhere between these two. This is 54. This is 86. Difference. Last two digits I'm reading, 54 and 86. 86 minus 54 will give me 32. 86 minus 54 will give me 32. 32 again divided into 2/3 range. Okay, 2/3 range. 32 if you divide into 3 parts, then it should be approximately 22. That 22 you add it to this, then that will give me the 0.7454 value. 0.7454 value. Okay, so you can take that 0.7454 value, and on the other side you can take the value of 1 minus 0.7454 and then subtract from 0.7454 the 1 minus that value. You will get some quantity there, and that quantity has to be multiplied with whatever we have got here, right? And whatever we have got here, and that we know this value, and we just found that value, and that will turn out to be this. So 7454 minus of 1 minus 7554, and this value is given to us as 615 squared divided by 0.4950, and that turns out to be 52775.2. Okay, and the root of that will be this quantity. So that's how we can solve this. If you have any doubts, you try to solve that, whether you're getting that. Okay, write down 615 square divided by 0.4950 multiplied by 7454 minus, is it 7454? Let me go back to the table. Okay, 7454 plus, okay, sorry, 7454 plus 22. Okay, because that 2/3 portion between this also should be considered. So that is 22 should be added with this. So 0.7476. So that will be the value. So using that, here what you need to do is you find this quantity where this is 615, and this quantity is nothing but 0.747, how much was that? 7476 minus 1 minus 7476. If you multiply all that, you should be able to get this value. Are you getting that or not is what you need to check, right? You need to check. Okay. Once you get this, then you can just take the root of that. Okay, so we are left with 5 minutes. If you have any doubts, you can ask. Okay, So let me use the calculator to find out that quantity. Hmm. So 1 minus 7, 4, 7, 6. Oh, I should write point, right? So 1 minus 0.747, 6. So I'll get this, right? So this should be subtracted from, again, that 7476. So minus I'll put here 0.7476. So I'll get this 45.4952. 0.4952. So what is there in the denominator of that? We get the same thing. You need to check 615 divided by this multiplied by that quantity. Will it be this? I think we are not getting. So where is it? We are doing the mistake. Divide that by root of 2 pi. Might be after that you will get this figure. 6115 multiplied by 615 square equal to divided by 0.495 equal to, so there is a minus there, which is okay, it's not this much, divided by, what is that, 2 pi, root 2 pi, is it? Memory save, multiplied by -1. No, it's not working out. Okay. So we need to check this over here. I'll stop the recording.